In this session, we will talk about the moment area theorems. So there are two moment area theorems, and these theorems become extremely useful when we have to find out the slope and deflection at a particular point on a beam. So when we are not interested in the variation of slope or deflection as a function of x, which is easy to find through, let's say, the double integration type approach, and we are interested in only one or two particular points on a beam where we want to find out the slope or deflection, the moment area theorems become extremely useful. So we start talking by theorem 1. So this basically, both of these are derived from the basic Euler-Bernoulli beam theory relation. So this relation EI phi equal to m, this is what comes from the basic Euler-Bernoulli theory, where phi is the curvature, m is the moment applied on a beam, moment at a section of a beam, and EI is the bending rigidity. Okay, so phi can be written as d theta by dx, where theta is the slope, and in turn this phi is the second derivative of deflection. So this basic equation we can recast, and we can write it as d theta by dx equal to m by ei. So basically for phi we have replaced it by d theta by dx, and then we have d theta as m by ei times dx, and then we can integrate from a point a to b of the beam. So basically we have integral a to b of d theta equals to integral a to b of m by ei dx, and this recall that this m by ei is nothing but phi, which is the curvature of the beam. So eventually we get a relation of this kind, where on the left hand side we have theta b minus theta a, or this sometimes is written as theta ba, and theta b minus theta a represents the change in slope as we move from a point a to b on a beam. Okay, and on the right hand side we have integral a to b m by ei dx. This is basically the area of the m by ei diagram between points a and b, and m by ei is also the curvature diagram. Okay, so if we let's just see it through a figure. So let's say there is a beam where there are 2 points a and b marked in red and green here, and it may have some loading condition, and we have drawn the m by ei diagram. So m by ei diagram can be simply drawn, first you draw the bending moment diagram and then divided by the ei of the beam. Now we assume that the red color line here is the tangent at point a, so that will have an angle theta a. So the slope at a particular point will be same as the slope of the tangent at that point. Similarly, the tangent at b is shown in green color in this, and let's say that angle of that tangent is theta b. So what the first theorem gives us is that, let's say if we start from point a, so we are starting at an angle theta a, and then from here we move towards point b, another point on the beam. So our angle started from theta a and it becomes theta b. So the overall change in angle, what we are calling theta ba, is the change in slope or change in angle as we go from point a to point b, right? So as we go from point a to point b. Okay, so when we are writing theta ba, what we are saying is we are starting from point a and we are going to point b. Okay, and this theta ba is representing the change in angle when we go from point a to point b. Okay, let's look at an example to see how this works out. So let's say we are given a cantilevered beam AB as shown with a tip load, and we are interested in finding, let's say, the slope at point B. So we have to find theta b. Okay, the some quantities which are required are given. So now we consider the deflected shape. So this AB, so this is going to be the deflected shape of the beam, right? And then we draw a tangent at A, which happens to be in this case a horizontal line, because at A theta equal to 0, and because it is a fixed support. And then we draw a tangent at point B, which is shown in green color. So if we integrate now the m by ei diagram, so if we integrate the curvature diagram from A to B, that will give us the change in slope when we go from the tangent at A to the tangent at B, right? So this is the theta BA that it will give. And since theta A is 0, this theta BA is also going to be theta B, right? So theta BA is equal to theta B minus theta A will be the area of the m by ei diagram between A and B. So basically all of this shaded area, right, this area is going to give us the change in slope, and this area can be simply calculated as this is the area of a triangle, so 1/2 times the height times the base. So this comes out as theta B. Now here what we've also done is theta A we have put equal to 0. Okay, so it comes out to be minus 0.01 radians, and we had also calculated it from the function that we can calculate, let's say, from double integration. So of course both will come out the same. Now one thing to notice here is that this comes out with a minus sign, and what it is indicating is that at the point B the rotation is clockwise. So rotation of point B is clockwise. Okay, let's look at one more example. We have a simply supported beam where there is a UDL being applied, and we have to find theta A, okay, slope at point A. Now if we draw the deflected shape, it is going to look like this, and on this deflected shape, since the loading and the boundary conditions are symmetric, we know that at the midpoint, which is a point C at L by 2, that is going to have the maximum deflection, and hence it is going to have 0 slope. So now we can consider 2 points as A and C, where the red line is the tangent at A and the green line is the tangent at C. Okay, so as we go from point A to point C, we start from point A and we reach point C, so we are talking about theta CA, which is the change in slope when we go from A to C. So that theta CA can be calculated as the area between A and C of the m by ei diagram, right? So this shaded area is what will give us theta CA, right? So theta CA becomes theta C minus theta A, which is the area of m by ei diagram between A and C. So that area comes like this. So this is a parabolic curve. So the area is 2 by 3 times BH. So this is 2 by 3 times B times H. So this comes out to minus 1.33 times 10 to the minus 3 radians, and again here theta C is 0, right? So this minus sign is coming because of that. So theta CA is actually minus theta A. Okay, so theta A becomes minus of the area, and hence we get that. And again here you see that theta A, so although theta CA here is positive, see, theta CA being positive means when we go from tangent at A to C, we are going in the counterclockwise direction. However, theta A, which is the angle of from horizontal of the point A, that is in clockwise sense, and we get that as negative. Now, a few points about the sign convention. One is that these angles are always computed in radians, and these will be extremely small. Okay, so sometimes there is a confusion that between A and C you can mark actually 2 angles. This is also an angle between A and C, and this is also an angle between A and C, tangents at A and C. But always keep in mind that these angles are extremely small, so the angles we are looking for will be essentially acute angles. They will be always less than 90 degrees. In fact, they will be close to a degree or even less, because we are dealing with small deformation problems. So if you look at the magnitudes also, what we found in the previous one was of the order of 10 to the power minus 3 radians, and the previous one was minus 0.01 radians. So these angles are going to be extremely small. So always look at the geometry of the problem and the potential deformed shape, and in general the acute angle between the two tangents is what this method is going to give. Okay, so always try to visualize the deformed shape, and from there you will be able to get the correct sense of the angle. Another thing to recognize is that we have considered sagging shape to be positive bending moment. So this will give positive curvature m by ei, and hence it will give positive area of m by ei diagram. Okay, and the hogging shape of deformation we are assuming, or we are considering as negative moment sign convention, and hence this will give a negative area of m by ei. So positive area gives positive theta, which comes out to the fact that counterclockwise angles are considered positive here. So this is again a convention. And negative area gives negative theta, which means clockwise angles come out to be negative by our convention. And another thing is that we're always going from A to B, where the point A is to the left of point B, right? So in the beam, point A is to the left, right? So in the beam, we are starting from a left point A, and then we are going to a point B. So we are starting from A, going to B. Okay. Now, if we have to go the other way, so for example, if we have to go, so this theta BA is where we are starting from A and going to B. If we write theta AB, which is we start from B and go to A, so this by property of the integration, you will see will come out to be minus theta BA, right? So in other words, if we start from B and go to A, this is what will give theta AB. Okay, and if we start from A and go to B, this is what is giving theta BA. And by the property of the integration, it is easy to see that theta BA will be equal to minus of theta AB. Okay, so this is one more small thing to be kept in mind with respect to sign conventions. Let's now move on to the second theorem. So the first theorem allows us to calculate slopes at any point, and the second theorem will allow us to calculate deflections at any point. So again, we consider a generic beam, again 2 points A and B on the beam, and there is a m by ei diagram also, or the curvature diagram. Now we consider a differential element dx, which is at a distance x from point B. Okay, so from point to the right, we are considering a distance x, and this is where the differential element lies, right? Now we have now one tangent at A. So this red tangent is tangent at A. Okay, and then we can now draw two more tangents. One this one is a tangent at x, and then this one is a tangent at x plus dx from B. Okay, so one tangent we are drawing for this point, one tangent we are drawing from this point. And if we consider the vertical distance between these two tangents at point B, so this distance we are calling d delta, right? Or this is the vertical distance between the tangents at x and x plus dx. Okay, and the angle between these two tangents, or the change in slope between these two tangents, is going to be d theta, right? So it's in a way like that, where this is d delta, this angle is d theta, and this distance is x. So basically what we can write is that d delta is x times d theta because of small angle considerations, and this d theta becomes phi times dx. Okay, so basically d delta becomes x times phi times dx. Okay, and now again, if we integrate it from A to B, basically what we're saying is that we start from here again and we go to point B, right? So eventually what this d delta will give us is the distance of point B from the tangent at A. Okay, and this we are calling as delta BA. So delta BA is the vertical deflection of point B from the tangent at A. Okay, so this is not the absolute deflection of point B. but this is the vertical deflection of point B from tangent at A. Okay, so basically we are doing integral a to b of d delta. This becomes integral a to b of x times m by ei dx. Okay, and and this type of integral, I believe you have seen, where you have integral of x times some kind of area, dx. This is in that spirit, right? So this becomes x bar b. So x bar b is the location of the centroid of the area of this shaded area from point B, and theta BA is this the shaded area, right? So theta BA we have seen earlier also. So delta BA can be calculated by x bar B times theta BA. Okay, and this x bar comes as a consequence of this integration. And you may try to recall the moment of inertia type integrals, where you get x dA or x squared dA, things like that. Okay, let's look at a few examples to see how this works out. So let's say again we are working with the same problem as example 9.1, and we have to find delta B now. So earlier we were trying to find theta B, right? So delta BA by our definition is the vertical deflection of point B from tangent at point A. So if this is tangent at A, from here to here the vertical deflection, this is what is delta BA. And since the tangent at A is horizontal, this delta BA also happens to be equal to delta B. Okay, so now delta B can be calculated as x bar B. So the from B, the distance to the x bar or the centroid, times theta BA. Now x B bar becomes 2L by 3, that is the centroid of a triangle, times theta BA. So eventually we get delta B as minus PL cube by 3EI, and putting in the values, there is a minus missing, so putting in the values we get this. Okay, now again the negative sign here is indicating that the point B has gone below the tangent. Okay, so it has gone below the tangent. So a negative sign of delta BA will indicate that point B has displaced below point A, below the tangent at point A, not point A, right? Okay, now let's look at one more example. So again the same simply supported beam. Now instead of theta A earlier, we want to find delta C. So by earlier logic we had concluded that tangent at C is going to be horizontal. So now if we consider delta AC, which is deflection of point A with respect to tangent at C, right? So that will be actually so now A is above C, so delta AC should come out to be positive, but we know that C is going below A, so delta AC should be equal to minus of delta C, right? So delta AC should be equal to minus of delta C. Okay, so delta AC becomes minus minus x bar A times theta AC. Okay, and now since we are writing here delta AC, here point A is to the left of C, so C is to the right of A, and hence we have this other minus sign where this is coming basically from the x bar A, right? So x bar A we are calculating from a left hand point, not from the right hand point. So this is, so delta AC becomes minus x bar A times theta AC. So when we convert theta AC to theta CA, this minus sign goes away, and theta CA we can calculate as the area, and x bar A again for a parabolic segment from the left hand, this comes out to be 5 by 8 times B. Okay, so delta AC comes out to be this. Now notice that delta AC comes out to be positive, which means that point A is above the tangent at C. Okay, and from here we can make it to delta C. So you may want to write it with a minus sign, or you may want to say that delta C is this much downwards. Let's look at an indeterminate problem also. So let's say there is a propped cantilever beam with an end moment m naught being applied, and we have to find all the support reactions, for example. So this can be broken down into two parts where, so first we have to find the redundant reaction. So let's take VB as the redundant reaction. So this breaks down into two cantilever beams, one with the real load and second with this redundant force, right? And so basically then what we want is that delta B overall should be 0. This is the compatibility condition. So we can get delta BA1 from the first, we get it negative because B goes below the tangent at A, and then we get delta BA2 which comes from the second one, and here we get it positive because it goes B deforms above the tangent at A. Now for compatibility we want both of them to be equal in magnitude, because one is going above, one is going below. So from here we can get VB equal to 3m naught by 2l, right? And once we have computed VB, we can find out the other support reactions like so. Let's say we had to also find theta B in this case, right? So that is also straightforward. So we know theta BA1 and theta BA2, right? And theta A is 0 in both cases. So theta BA will be theta B, and if we add them with their respective signs, so theta BA comes out to this and theta BA2 comes out to this. So if we add them with their signs, what we can get is theta B, and the fact that it comes out to be negative means it is clockwise. And because of this moment, you can also visualize that the deformed shape is going to be like this, where theta B is a clockwise rotation. Maybe we can extend this further. We can say we want to find the deflection at the midspan, let's say at a point C. Okay. Now again, we can calculate the deflection in both 1 and 2 cases and then add them up with their respective signs. That will be the total deflection at point C. So delta C1 is nothing but delta CA1, right? So delta CA will be deflection of point C with respect to tangent at A. So that is x bar 1 C times theta CA1, right? So that comes out to be this in downwards. And delta C2 will come from the second one. Okay. We are interested in this portion, so that area is comprising of a rectangular area and a triangular area. So that will be, the composite centroid areas will be used. So eventually delta C2 comes out to this, and this is coming to be upwards because it has a positive sign. So we add them with their respective signs. So eventually we get m naught L squared by 32 EI. And since this comes out with a positive sign, we know that this is an upward displacement. And if you look at the deformed shape, so C is going to be somewhere here. So it is basically deforming upwards from the baseline. Okay. There can be one more type of complication where different portion of beams have different EIs, right? So this is also straightforward. So the bending moment diagram is like this, but the curvature diagram will become different because different segments here will be multiplied, will be divided by different numbers. So this one is being divided by EI, whereas this one is being divided by 2 EI. So the curvature diagram becomes like this, and eventually all the calculations remain the same, right? We can have one more type of problem where, let's say, we don't know where the maximum is. So let's say this kind of a beam is given and we want to find what is the maximum displacement of the beam, right? So in this case we don't know where it will be maximum, so we assume that there is a point D at a distance, let's say xm, where the maximum displacement happens. And since the maximum displacement happens here, the tangent at D will be horizontal. Okay, the curvature diagram looks like this. Okay, so now we can do some pre-calculations. So delta CA which is deformation of point C with respect to tangent at A, right? So if this is tangent at A, this is delta CA. So this delta CA can be calculated. Okay, delta CA will be from C we will consider centroids and multiply by respective areas and add them up. And delta CA can also be calculated as theta A times L, because theta A is a small angle, so theta A times L will also be delta CA. So from here, we can calculate what is theta A. Okay, and then we consider theta dA. Theta dA is the change in slope when we go from point A to point D. Okay, and we know that theta dA can be calculated as the as this area, shaded area, and we also know that theta d is 0. So theta dA is going to be equal to theta A, which we have calculated from above. So this theta dA comes out in terms of xm, and from theta A, we can calculate what is xm, and once we have calculated xm, we can calculate delta max, which is delta AD. Okay, so delta AD will be x bar A times theta AD. So that comes out to be this. Okay, so you see that in this way, this method is very powerful when we have to calculate slopes and deflection at a particular point. And this becomes extremely useful when we are not interested in the overall variation, but only at a few points, slope and deflection of a beam.